Welcome to the AI Coach by Anil Nathu. Hello and welcome to the Deep Dive. We're the place you turn to when you want to really get under the hood of the big research shaping our world. Today we're tackling something truly fascinating and honestly pretty critical in the world of AI. We're going deep on why large language models, LLMs sometimes, hallucinate.
That's the term everyone uses, yeah.
Right. It's like these incredibly smart AI systems suddenly start making things up. They sound so confident, so plausible, but the information's just wrong, completely false sometimes.
We've all seen it happen, haven't we? You ask a question, get a smooth answer, and then, wait a minute, that's not right at all.
Exactly. And today, we're not just going to, point at the problem. We're launching a real deep dive. We want to understand the roots of this. Why does it happen?
And that framing is spot on, because it's really important right at the outset to be clear about what hallucination means here. It's not like human perception, not like seeing things that aren't there.
Right. It's an analogy, but maybe a slightly misleading one.
It can be. In AI, it's fundamentally different. We're not talking about consciousness or imagination. It's more, well, it's a statistical thing. It's an outcome, often predictable, based on how these models are built, how they learn from massive amounts of data, and maybe most importantly, how we test them, how we evaluate their performance.
Okay, so statistical, not psychological.
Exactly. Understanding that distinction is absolutely key if we want to really grasp the problem and, actually find solutions.
And to help us navigate this, we're grounding our discussion in some serious research, a paper that really cuts through the noise with some rigorous analysis. We're diving into a recent OpenAI paper called Why Language Models Hallucinate. The authors are Tauman, Kalai, Ofir, Nachum, Santosh, Vempala, and Edwin, Zhang. This isn't just like a blog post with opinions. It's a deep mathematical look at the issue.
And it comes to some pretty surprising conclusions, actually.
So our mission today really is to unpack what this paper tells us.
Yeah, we want to get at the statistical drivers behind these errors. Why do they happen in the first place? And then, crucially, why do they stick around? And what can we actually do about it? The paper proposes some really interesting socio-technical solutions.
Socio-technical, meaning not just code fixes.
Right, involving how we humans interact with and evaluate these systems, too. And this understanding, it's essential for anyone relying on AI, anyone building with AI, and definitely relevant for folks using tools like AI Coach by Anil Nathu to get the most accurate, reliable results from AI.
Okay, so let's nail down the definition first. When we say hallucination in the context of LLMs, what are we really talking about?
The paper defines it pretty clearly. It's the generation of overconfident, plausible falsehoods.
Overconfident, plausible falsehoods. Okay, break that down.
Right. So falsehoods, they're just incorrect statements. But plausible is key. They sound reasonable. They fit the context. The grammar is right. They seem like they could be true.
Unlike just random gibberish.
Yeah. Exactly. And overconfident is the other crucial part. The model presents this false information with the same level of certainty, the same fluency, as it presents actual facts. There's often no hint of doubt.
And that's what makes them so tricky, isn't it? They're not obvious errors. They sneak in.
Precisely. It's not just a minor glitch. It's this deep characteristic that makes it really hard to trust these systems completely. It really limits their usefulness if you can't rely on the core information they give you.
So it undermines the whole value proposition sometimes.
It absolutely can. And again, these aren't like human perceptual errors. The paper stresses these are statistical outcomes.
Can you give an example? Something concrete from the paper?
Yeah, there's a really telling one. One of the authors, Kalai, the researchers asked a state-of-the-art open source model for his birthday.
Okay.
And they were very specific in the prompt. They said, basically, only answer if you know it for sure, and asked for the DDMM format.
So explicitly told it not to guess.
Explicitly. And what happened? On 3 separate tries, the model gave 3 different, totally incorrect dates. 0307, 1506, 0101.
Wow. And none were right.
None. The paper mentions his actual birthday is in the autumn. So the model didn't just make one mistake. It confidently asserted different falsehoods each time. It was essentially bluffing, repeatedly.
That really highlights the problem, doesn't it? It doesn't know that it doesn't know.
Exactly. And it chose to invent answers instead of admitting uncertainty.
Was there another example like that?
Yes. They also tested different popular LLMs models like ChatGPT's, GPT-4o, DeepSeek, Llama on another fact about Kalai, the title of his PhD dissertation.
Okay, another specific verifiable fact.
Right. His actual dissertation was from 2002 at Carnegie Mellon University. But the models, they came up with completely wrong titles and wrong universities and wrong years.
Like what?
Well, for instance, DeepSeek's model said the title was Algebraic Methods in Interactive Machine Learning, supposedly from Harvard in 2005. Totally wrong.
Completely fabricated.
Completely. Llama said it was Efficient Algorithms for Learning and Playing Games from MIT in 2007. Again, nowhere near the real title. Boosting Online Algorithms and Other Topics in Machine Learning from CMU in 2002.
It's not even close. It's like they're just combining plausible-sounding academic words.
Pretty much. And presenting it as fact. It's a full-blown fabrication delivered with complete confidence.
So these examples help us see different types of hallucinations too, right? The paper makes a distinction.
It does. They talk about intrinsic hallucinations. These are errors that contradict something right there in the prompt or information given in the same conversation.
Okay, like what?
The paper gives this great example. Asking a model, how many D's are in the word DeepSeek? You can see the word right there.
Right, there are two Ds, Evie.
You'd think. But models like DeepSeek v3 sometimes answer 2, sometimes 3, and some tests even got answers like 6 or 7.
Seriously, 6 or 7 Ds in DeepSeek.
Yep. The model is directly contradicting the information right in front of it. That's intrinsic.
Okay, and the other type?
That's extrinsic hallucinations. These contradict the model's broader training data or just, facts about the real world. The birthday example, the dissertation title, those are extrinsic. They're wrong based on external reality, not just the immediate prompt.
Got it. Intrinsic is self-contradictory within the conversation. Extrinsic contradicts the outside world.
Exactly. It's a useful distinction for understanding where the errors might be coming from.
So, after looking at all this, what's the big takeaway from the researchers? Why do these happen? Is it just a bug they haven't fixed yet?
This is where it gets really interesting and maybe a bit unsettling. The paper argues hallucinations aren't really a bug in the traditional sense, not like a coding error you can just patch.
Not a bug. Then what are they?
They argue it's more like a feature.
A feature? That sounds wrong.
Mm-hmm.
Who would want hallucinations?
Well, not intentionally want them, obviously, but they argue it's a direct, statistically predictable consequence of how LLMs are currently designed, trained, and, this is the really crucial part, how they're evaluated. The way we build and test them actually leads to this behavior.
Okay, that's a huge claim. Not a bug, but a feature arising from the process.
It's a major shift in perspective. The paper lays out this powerful two-part argument. First, hallucinations start as basically errors in binary classification way back during pre-training, just natural statistical noise and learning limitations.
Okay, errors start early.
Right. But then second, these errors don't get stamped out. They persist and can even get worse during post-training because our evaluation methods are, well, the paper calls them misaligned.
Misaligned.
They unintentionally end up penalizing models for being honest about uncertainty, for saying, I don't know. And by doing that, they inadvertently reward confident guessing.
Ah, so the testing itself encourages the behavior we don't want.
That's the core argument. It's a systemic issue needing a systemic solution, not just tweaking the code. And understanding this is vital for anyone using AI, especially if you're relying on tools like AI Coach by Anil Nathu for high-stakes applications where accuracy is non-negotiable. It reveals the deep challenges we need to tackle.
Okay, let's start at the beginning then. Pre-training. This is where the magic happens, right?
Mm-hmm.
The model learns language from just tons of text.
Mm-hmm.
Books, websites, articles.
Billions, sometimes trillions of words. It's learning the patterns, the grammar, the facts embedded in all that text, learning the distribution of language, as they say.
Right. And here's the part that really grabbed me from the paper. They say even if the training data was perfect, absolute pristine, no errors at all, the model would still generate errors just because of the statistical goals of pre-training.
It's counterintuitive, isn't it?
Totally. My first thought is perfect data in, perfect model out. Why isn't that true?
It's a really common assumption, but the authors show why it's flawed. Think about what a model that never makes an error would look like. It could just say, I don't know, anytime it wasn't 100% certain. Or it could just perfectly memorize the error-free data it saw and never try to generalize or say anything new.
Right, but that wouldn't be very useful.
Exactly. It wouldn't hallucinate, but it would fail at the main goal, which is density estimation. That just means understanding the underlying probabilities of language, how words and concepts fit together well enough to generate new, plausible text that fits that pattern.
So to actually be useful, and generate novel text, it has to take some risks.
It has to explore the possibilities based on the patterns it learned. And when it does that, especially with facts or relationships that are rare or ambiguous in the data, it inevitably risks making errors. It's not just about bad data polluting the system. It's inherent in the statistical process of learning something as complex as language.
Okay, so more data or cleaner data helps, but it won't eliminate the problem entirely because of the statistics involved.
That's the key insight. It challenges that simple, more data is corsict model idea. It's a deeper statistical hurdle.
So if errors are kind of baked in statistically, how do we get a better handle on them? The paper introduces this idea of the is it valid classification problem, the A to V thing. What's that about?
Think of it like this. As the model is generating text, for every potential word or phrase it considers adding, it's doing a quick internal check. Is this a valid continuation? Does this fit the language patterns I've learned? It's making countless tiny yes-no decisions valid, plus, or error.
Okay, like an internal quality control check.
Sort of. And the paper points out that actually generating good, coherent text is statistically harder than just making those individual yes-no validity judgments. Because to generate a whole sentence, it has to get all those little validity checks right along the way.
Ah, I see. One wrong turn and the whole thing can go off the rails.
Exactly. And they found a mathematical link. The rate at which the model actually generates errors, the hallucination rate you see, is roughly greater than or equal to twice the rate at which it messes up those internal is it valid checks.
Twice? Why twice? That seems high.
Well, think about generating a sequence. You make a choice, then another, then another. If you make even one misjudgment on validity early on, it can throw off everything that follows. It's like a cascade effect. A single internal misclassification can lead to a full-blown generative error.
Okay, so small internal mistakes get amplified in the final output.
That's a good way to put it. It shows that the same basic statistical factors that cause errors in simpler classification tasks, like telling cats from dogs, are also at play in causing these complex LLM errors. It's all rooted in statistical learning limitations.
This connects to another concept they discuss, calibration. What does that mean here?
Calibration is about how well the model's stated confidence matches its actual accuracy. If a model says it's 80% sure about something, is it actually correct 80% of the time when it says that? If yes, it's well calibrated.
Okay.
Now, here's the twist. The paper argues that base models, before all the post-training adjustments like RLHF, are often surprisingly well calibrated. Their internal confidence scores actually reflect their true accuracy pretty well.
That sounds like a good thing, right?
It is, in a way, but it has a consequence. If a model is well calibrated and it encounters a fact that's genuinely unlearnable or extremely rare in its data, its calibration demands that it expresses low confidence or it makes an error.
Wait, so being well calibrated forces it to make errors sometimes?
On things it truly doesn't know or can't reliably infer from the data, yes. If it confidently asserted an answer for something it only had a 10% chance of knowing based on the data, it wouldn't be well calibrated anymore. So to maintain calibration, it has to reflect that uncertainty, which often manifests as either saying, I don't know, which base models aren't always trained to do explicitly, or making an error.
The paper actually points to studies, like with GPT-4, showing this calibration is pretty good before reinforcement learning kicks in. That's fascinating.
It is. It means errors aren't just random noise. They're a natural, even necessary consequence of trying to accurately model the probabilities learned from the data using standard methods like minimizing cross-entropy loss.
Can you quickly explain cross-entropy loss for us?
Sure. Think of it as the score the model gets during training. It measures how surprised the model is by the actual next word in a sentence compared to what it predicted. If it predicts cat with high confidence, but the real word was dog, it gets a high loss score, a penalty. The whole goal of pre-training is to minimize this loss, to make its predictions match reality as closely as possible.
And even doing that perfectly leads to errors.
The paper shows that optimizing this very objective inherently creates the conditions for certain statistical errors to emerge, which we then see as hallucinations.
So the takeaway for you, the listener, is pretty stark. Expecting a model trained this way to be both perfectly calibrated and always correct is, well, statistically unrealistic right now. It's a fundamental trade-off baked into the current system. It's not just about fixing bugs, it's about the core training philosophy, something vital for platforms like AI Coach by Anil Nathu to grapple with, #tag_B. Specific factors driving pre-training errors. Okay, so errors are statistically inevitable during pre-training. Let's drill down into the specific reasons the paper gives for why these errors happen then. First up, arbitrary fact hallucinations, the no pattern problem.
Right. This relates to what's called epistemic uncertainty. That just means the model lacks the necessary knowledge because it simply wasn't in the training data or wasn't there clearly enough to learn a reliable pattern.
Like the birthday example again.
Exactly. The paper calls things like birthdays arbitrary facts. There's no logical rule or pattern that dictates someone's birthday. It's just a random specific piece of information. It's not like learning birds fly where there's a general concept. A birthday is just a fact.
So, if the model hasn't seen Adam Kalai's specific birthday mentioned clearly and maybe multiple times in its training data,
it has literally no basis to figure it out. It can't deduce it. It can't infer it from other birthdays. The information is either there to be recalled or it's not.
and if it's not there, or only there very weakly, the model is forced to guess if prompted.
Pretty much. And that guess, presented confidently, is a hallucination. It stems from the absence of a learnable pattern for that specific arbitrary fact.
To quantify this, they use this idea of the singleton rate, right?
Yeah.
Based on Alan Turing's work.
Yeah, it's a really neat connection. Think about all the unique facts in the massive training data set. The singleton rate is simply the fraction of those facts that appear only once. Just one single mention in trillions of words.
Okay, so facts that are really rare in the data.
Exactly. And the paper establishes this important relationship. The baseline hallucination rate you can expect after pre-training is at least as high as this singleton rate.
Can you quote the paper's example on that?
Sure. They say, for instance, if 20% of birthday facts appear exactly once in the pre-training data, then one expects base models to hallucinate on at least 20% of birthday facts.
Wow. So the rarity of facts in the training data directly predicts a minimum level of hallucination for those kinds of facts.
It gives you a mathematical handle on it. If you know your data has lots of singletons for certain topics, you should expect the model to struggle and likely hallucinate on those topics. This is super relevant for anyone tuning models or building knowledge bases, like the systems behind AI Coach by Anil Nathu. Understanding your data structure is key to anticipating errors.
Okay, so that's arbitrary facts. What's the next factor? Poor models. This sounds like the model itself is just not good enough.
Yeah, this is about situations where the model's architecture, its fundamental design, isn't capable of capturing certain patterns or relationships no matter how much data you feed it.
Can you give an example?
The paper uses a great historical example, trigram language models. These were common back in the 80s and 90s. They work by predicting the next word based only on the previous two words. A very short memory, basically.
Okay, 2 words. That's not much context.
Not much at all. Now imagine these two sentences. She lost it and was completely out of versus he lost it and was completely out of.
Right. The natural completion depends on she or he. You need her mind or his mind.
Exactly. But the pronoun needed, her or his, depends on the word she or he, which is more than 2 words back from the end.
Ah, so the trigram model, looking only 2 words back out of, has no idea if the subject was male or female.
Precisely. It literally cannot access the information needed to make the correct choice. The paper states such a model must have a generation error rate of at least 12 on this kind of task. Its architecture is just too limited, too poor to capture that grammatical dependency.
So errors can come from the model design itself, not just the data.
Absolutely. And we see echoes of this even in modern LLMs.
Like the letter counting example, counting Ds in DeepSeek.
Yeah, that's a good contemporary example. DeepSeek v3 struggled with that, remember, giving answers like 3, 6, or 7. But a more advanced reasoning model, DeepSeek R1, got it right consistently because it used a step-by-step reasoning process, basically spelling it out internally.
So why did the first one struggle?
It suggests a representational challenge. LLMs don't see letters like we do. They see text broken down into tokens, which might be whole words or parts of words. Counting individual characters within those tokens requires an extra layer of processing or reasoning that the base model might lack. Its representation makes the task harder than it looks.
So the way it thinks about text makes certain simple tasks difficult, leading to poor model errors.
Exactly, and it shows how different architectures or adding reasoning capabilities can sometimes overcome these limitations.
Okay, arbitrary facts, poor models. What else contributes to pre-training errors according to the paper?
They touch on a few other important factors. One is computational hardness. This is a fundamental limit. AI models can't just break the laws of computer science, right?
Right, some problems are just inherently incredibly difficult to solve.
Exactly. The paper uses the analogy of trying to decrypt a secure message without the key. An LLM asked to do that will just generate garbage, essentially hallucinate, because the task is computationally intractable without the key. It's not about data or architecture. The problem itself is too hard. This applies to any task where finding the correct answer requires solving a computationally hard problem.
So if a prompt implicitly asks the model to do something computationally infeasible, it's likely to hallucinate an answer instead.
It's a source of unavoidable errors in those cases. Another factor is distribution shift, or out-of-distribution data.
This is when the questions you ask the model are really different from what it saw in training.
Precisely. If you train a model mostly on news articles and then ask it to write poetry, or you train it on simple facts and ask it complex riddles, its performance might degrade. It's outside its learned distribution. The paper gives the example. What's heavier, a pound of feathers or a pound of lead?
The classic trick question.
Right. If the model hasn't seen many questions like that, which play on common sense versus literal meaning, it might default to the pattern lead is heavy and get it wrong. A significant shift from its training data increases the chance of errors.
And the last one feels obvious, but crucial. GI go, garbage in, garbage out.
The oldest rule in computing, right? And it absolutely applies here. The huge data sets used for pre-training are scraped from the internet, mostly. They are full of errors, biases, misinformation, outdated facts, conspiracy theories, you name it.
So the models learn the good stuff, but they also learn the garbage.
They learn the statistical patterns of all the texts they see, including the errors. If a misconception or a falsehood appears frequently, the model will likely learn it and reproduce it, often with high confidence because it saw it so much. It just reflects the noise and flaws in its input data. This is a huge ongoing challenge for data curation.
Okay, so pre-training sets the stage with these inherent statistical errors, architectural limits, computational boundaries, data shifts, and just plain bad data.
Yeah.
That's a lot to contend with even before we try to fine-tune the models.
Exactly. It shows that hallucinations have deep roots in the very foundation of how these models are created.
All right, so we've seen how hallucinations get started during pre-training, but then there's post-training, right? Things like RLHF reinforcement learning from human feedback, which are specifically designed to make the models better, safer, more helpful, less likely to hallucinate.
That's the goal, absolutely.
So why do hallucinations still persist? Why don't these post-training methods just wipe them out? The paper uses this really interesting analogy about humans taking tests.
Yeah, it's a very intuitive way to frame the core problem. Think about being a student taking a multiple choice test. You come to a question you're really not sure about. What do you do?
Well, there's no penalty for wrong answers, I guess. If leaving it blank gives me 0 and guessing might get me points, I guess.
Exactly. You do the calculation, maybe subconsciously. A guess has a chance of being right. Leaving it blank has 0 chance. So purely from a score maximizing perspective, guessing is the rational strategy when uncertain if there's no penalty for being wrong.
Okay, I see where this is going.
The paper argues that LLMs are basically evaluated using the same logic. Most benchmarks use a binary 0-1 scoring scheme. 1 point if the answer is deemed correct, 0 points if it's incorrect, or sure if the model says, I don't know, IDK.
So IDK scores the same as a wrong answer 0.
In many, many influential benchmarks, yes. And under that system, just like the student, the model learns that guessing always maximizes its expected score when it's uncertain. Even if it only has a tiny, say, 10% chance of being right, guessing yields an expected score of 0.1, while saying IDK guarantees 0.
So the optimal strategy for the model, purely based on score, is always guess if unsure.
Precisely. The paper says LLMs are always in test-taking mode because most evaluations are not aligned with the goal of truthfulness or accurately reflecting uncertainty. The incentives are skewed towards producing an answer, any answer, over admitting ignorance.
It's like we've accidentally trained them to be confident bluffers because that's what gets the highest score on our tests.
That's a very good way of putting it. And the paper doesn't mince words. It calls this an epidemic of penalizing uncertain responses.
Yeah.
Think about 2 models, Model A and Model B.
Okay.
Model A is perfectly honest. If it knows, it answers correctly. If it doesn't know, it says IDK and never hallucinates. Model B has the same knowledge as A, but it never says IDK. When it's unsure, it just takes its best guess, confidently.
Right.
Now, you test both on a standard benchmark with 0-1 scoring. Which one gets the higher score?
Well, Model B, the guesser, right, because its guesses will sometimes be right, adding points, while Model A gets 0 for its honest IDK answers.
Exactly. The paper states this clearly. Model B will outperform A under 0-1 scoring. This is huge. It means our current benchmarks, the very tools we use to measure AI progress, are actively rewarding the less trustworthy guessing model over the honest one.
That really changes how you should look at those AI leaderboards, doesn't it? A top score might not mean most knowledgeable and trustworthy. It might just mean best guesser under current rules.
It absolutely should make us more critical. It highlights why focusing solely on benchmark scores can be misleading, and why initiatives focusing on true accuracy and reliability, like those potentially integrated into AI Coach by Anil Nathu, are so important. We need evaluation methods that reflect the trustworthiness we actually want. #TAG evidence from current evaluation benchmarks.
So the paper claims most benchmarks penalize uncertainty. Did they back this up? Did they actually look at the popular evaluation?
They did. They conducted what they call a short meta-evaluation analysis, basically examining the scoring rules of several influential benchmarks used to rate LLMs.
And what was the verdict?
The findings were pretty consistent and support their claim. They found the vast majority of popular evaluations have binary grading. It's either right or wrong. And crucially, most offer none or only partial credit, if any, for saying, I don't know, or expressing uncertainty.
So the evidence suggests the test-taker incentive is widespread in practice.
Yes, it seems to be the norm rather than the exception. This structure fundamentally pushes models toward giving confident answers, even if they have to invent them.
Which means just adding a few specific hallucination tests isn't enough, is it? If the main benchmarks still reward guessing.
That's exactly the author's point. You can't just tack on a side test for honesty. The primary evaluations, the ones driving development and competition, the big leaderboards everyone watches, those need to change fundamentally. Otherwise, models will just optimize for the main score, which means guessing when unsure.
Can we walk through some of the specific benchmarks they mentioned to see how this plays out?
Absolutely. They give several clear examples. MMLU Pro and GPQA. These are massive multiple-choice tests covering tons of subjects. Think of them like the SATs for AIs. The paper notes, they're graded just like standard multiple-choice tests. No IDK option. You have to pick an answer. Guessing is incentivized.
Okay. Straightforward binary scoring.
Right. Then there's IFEVL. This tests if models can follow specific instructions like summarize this text in under 50 words without using the letter E.
Tricky instructions.
Yeah. And again, there's no explicit option to say, I can't follow that instruction reliably. So the model is pushed to try, even if the attempt involves hallucinating a way to meet the constraint or just failing in the attempt. Not trying is penalized.
Better to try and fail or hallucinate than admit defeat.
Seems to be the incentive. Then OmniMath for math problems. It might accept different forms of the right answer, like 1.5 or 32, but it doesn't give credit for saying, I don't know how to solve this. Again, encourages attempting a solution, even if it's wrong.
Okay, seeing a pattern here.
Definitely. WildBench is particularly interesting. It uses human graders on a 1-10 scale. But the actual grading rubric they looked at suggested an IDK response might get a score of 3 or 4, while a response that's just fair but contains factual errors or hallucinations could score higher, like 5 or 6.
Wait, so hallucinating could literally score better than being honest about not knowing?
According to that specific rubric example, yes. It directly rewards taking a shot, even if it's inaccurate, over admitting uncertainty.
That's perverse, really.
It highlights how even human judgment and evaluations can be structured to reinforce the problem. Then you have SWE Bench, a big one for coding. Models try to fix software bugs. It's graded on pure binary accuracy. Does the code patch pass the tests? Yes or no?
So an incorrect patch is the same score as no patch, or saying, I'm not sure.
Exactly. 0 points either way. No incentive to express uncertainty about a fix.
And even humanity's last exam, HLE, designed for the very top models.
Same story. According to Baker, primary metric, binary accuracy. They explicitly state it offers no credit for IDK. Even at the highest level of AI testing, the incentive is to guess rather than show awareness of limitations.
So for you listening, this is really critical context. When you see AI performance reports or leaderboard rankings, remember this underlying dynamic. High scores often reflect success within a system that implicitly rewards guessing over cautious honesty. It's why understanding the evaluation methodology is so important, something to keep in mind when considering any AI tool, including how AI coached by Anil Nathu might approach validation. Okay, so the diagnosis is pretty clear. The evaluation system is fundamentally misaligned, rewarding guessing over admitting uncertainty. So what's the cure? The paper proposes this socio-technical mitigation, focusing on confidence targets. What does that actually mean?
It's a really elegant and practical idea, actually. It's about changing the scoring rules directly within the evaluation prompts. Imagine adding a sentence to every question, something like this. Answer only if you are more than, say, 75% confident, T 0.75. Mistakes will be penalized 3 points, calculated as T1T. Correct answers get 1 point, and saying, I don't know, gets 0 points.
Okay, so you explicitly state the confidence threshold required to answer, and crucially, you introduce a penalty for wrong answers that's linked to that threshold.
Exactly. Let's use that T 0.75 example. Correct answer is +1, IDK is 0, and incorrect answer is an answer 3. Now, the model's internal calculation changes drastically.
How so?
If the model thinks it only has, say, a 50% chance of being right, guessing gives it an expected score of 0.51 plus 0.533 minus 0.51.5 minus 1.
Minus 1.
Yeah.
And saying IDK gets 0.
Right. So now if its confidence is below the 75% threshold, the statistically optimal strategy is to say IDK because 0 is better than minus 1. It completely flips the incentive away from low confidence guessing.
That's clever. It uses math to force honesty, essentially.
It aligns the model's score maximizing behavior with our desire for it to only answer when reasonably confident. And the beauty, the paper argues, is the statistical ramifications. With this clear threshold and penalty, there's one optimal behavior for any model aiming for the best score. Say IDK, if your internal probability of being correct is less than T.
It creates a clear, objective standard.
Yes, it supports objective grading and helps everyone, developers, evaluators, agree on how a model should behave when uncertain. It removes that ambiguity that currently favors guessing.
And a key part of their proposal is to put this into the existing big benchmarks, right? Not just create new niche ones.
Absolutely critical. They argue that just adding new, separate hallucination evils won't fix the core issue because models will still prioritize the main binary scored benchmarks.
Yeah.
But if you modify established evaluations like MMLU or SWE bench with these confidence targets,
Then you change the game everywhere.
exactly. It reduces the penalty for appropriate expressions of uncertainty across the board. And doing that might actually make specific hallucination-focused evaluations more effective because models won't be punished on the main leaderboards for exhibiting the honest behavior those niche evils are looking for. It's a systemic fix.
This connects to their idea of behavioral calibration. What's that distinction?
So, typical calibration might involve asking the model to output a probability score, like I'm 80% confident. Behavioral calibration is different. It's about evaluating whether the model acts according to a given confidence threshold T. Can it formulate the most useful response while being at least T confident in its correctness?
So it's about the action answering, you're saying IDK, based on the required confidence, not just stating a number.
Precisely. It's more practical to evaluate. Did the model answer when its confidence was likely above T? Did it abstain when below T? It avoids tricky issues like how to score a slightly inaccurate probability number or the infinite ways a correct answer could be phrased. It focuses on the decision-making behavior related to uncertainty.
It feels like a much more measurable and objective way to assess if the model knows when it doesn't know.
That's the goal. It's a proactive step towards building AI systems that are not just knowledgeable but also demonstrably aware of their own limitations, a crucial factor for building trust, especially for users of platforms like AI Coach by Nathu who need reliable outputs. #tag3, nuances, limitations, and the path forward. #A. Understanding the framework's scope and real-world complexities.
Okay, this framework feels really powerful for understanding and potentially fixing hallucinations. But the authors are good scientists. They acknowledge limitations and complexities. What are some of the nuances we should keep in mind?
Yeah, it's important to see the boundaries. For instance, the framework mainly focuses on plausible falsehoods. It doesn't spend much time on models generating complete nonsense or gibberish.
Which isn't a huge issue with the best models today, right? They usually sound coherent.
Exactly. State-of-the-art models rarely produce truly nonsensical strings. So, focusing on plausible falsehoods targets the more subtle and dangerous type of error. But it's good to remember the framework isn't primarily about stopping utter gibberish.
What about really open-ended questions, like asking for a biography or a story? How does the framework handle those?
It can apply. The definition of error could simply be, does the generated text contain any falsehoods? If a biography has even one wrong fact, the whole output is technically an error under this binary view.
But that feels a bit blunt, doesn't it? A single minor error isn't the same as a completely fabricated story.
It is blunt, and the authors acknowledge that. In reality, we often think about degrees of hallucination. The current framework simplifies things by sticking to a binary correct or contains error doesn't contain error definition for mathematical clarity. Handling those degrees of severity is an area for future work.
Okay, now a lot of people think adding tools like web search RAG, retrieval augmented generation, or better reasoning will just solve hallucinations. What does the paper say about that?
They definitely see value in RAG and reasoning. They can reduce hallucinations significantly by providing external grounding or better internal checking, but they're not a silver bullet
Why not?
because the core incentive problem remains. The paper emphasizes that even with RAG, the binary grading system itself still rewards guessing whenever search fails to yield a confident answer. If the search comes back empty or ambiguous, the model is still pushed to guess by current evaluation methods.
So a RAG helps when it finds something definite, but doesn't fix the guessing incentive when it doesn't.
Exactly. Plus, RAG might not help at all with intrinsic hallucinations like the miscalculations in the letter counting example. Those stem from internal processing limits, not a lack of external facts. So, helpful tools, yes. Complete fix, no.
The paper also mentions subtleties like latent context. What's that about?
This is about information that's not explicitly in the prompt or the response, but affects whether the answer is considered correct. Imagine you ask about phones, thinking about old landlines, but the model assumes you mean modern smartphones and answers based on that.
Is the model's answer technically a hallucination then? It's factually correct about smartphones, but wrong for your unstated context.
It's ambiguous, right? The paper's framework for simplicity doesn't really account for this hidden user intent or latent context. It focuses on the explicit text. This is another real-world complexity.
And they talk about the limits of just having correct, incorrect IDK as options.
Yeah, they call the simple correct, incorrect a false dichotomy, and adding IDK creates a false trichotomy. While IDK is way better, it's still a very simplified view of how humans express uncertainty.
Because we don't just say IDK, we hedge, we qualify.
Exactly. We say things like, I think maybe it's possible that as far as I know, we omit details we're unsure of, or we ask clarifying questions. There's a whole spectrum. The field of pragmatics, how context shapes meaning, is super relevant here.
So ideally, evaluations would capture all that nuance.
Ideally, yes. But that's incredibly hard, maybe impossible to do objectively and at scale. That's why the paper argues that introducing explicit confidence targets is a practical, objective improvement, even if it doesn't capture the full richness of human uncertainty expression. It's a step in the right direction.
And they mentioned that asking models for explicit probability scores, like I'm 73.5% sure, can feel unnatural.
Yeah, it can be weird, like the example, I'm 1365 certain that Kalai's birthday is March 7th. That's just not how people talk. So the paper focuses more on the top-level decision of what is said, the choice to assert, hedge, or abstain, rather than demanding precise, potentially awkward probabilistic statements. Hashtag be key takeaways and future direction.
Okay, let's wrap our heads around the main messages here. The big takeaway seems to be hallucinations aren't magic or mystery. They have concrete origins.
Absolutely. The core message is that they start as generative errors that parallel misclassifications in supervised learning right back in pre-training. It's a statistical phenomenon.
Driven by optimizing standard training goals like cross-entropy loss.
Right. And then these statistically inevitable errors are allowed to persist, even encouraged by the misaligned incentives baked into our current evaluation benchmarks, which reward guessing over honesty. It's a two-stage problem. Statistical origin, then misaligned reinforcement.
And fixing this isn't just about small tweaks. The paper contrasts trying to fix specific verbal tics, like models overusing the word certainly.
Yeah, referring to that Amadei and Friedman work.
Contrast that with a much bigger systemic problem here.
Yeah.
They state pretty bluntly that the majority of mainstream evaluations reward hallucinatory behavior. It's foundational.
And that's why their proposed solution is also foundational. They argue that making simple modifications of mainstream evaluations, like adding confidence targets and penalties, can genuinely realign incentives.
Rewarding models for showing uncertainty appropriately instead of penalizing them.
Exactly. And doing that, they believe, can remove barriers to the suppression of hallucinations. It could foster the development of more sophisticated, nuanced language models that have better pragmatic competence models that are better at communicating what they know and, just as importantly, what they don't. This kind of research is crucial for guiding the development of truly reliable AI, which benefits everyone, including users of platforms like AI Coach by Anil Nathu.
It's about building AI that isn't just capable, but also credible and trustworthy.
That's the ultimate goal.
So we've gone deep into the problem and the proposed solutions. Let's make this really practical now. What's the action plan? What should AI developers and researchers do? And what can you, our listener, do, whether you're using AI individually or in your business?
Okay, for the folks building and researching these models, the first clear action is adopt explicit confidence targets and benchmarks. This means really taking the paper's suggestions seriously and integrating these confidence thresholds and penalty structures into evaluations. Not just new ones, but modifying existing influential benchmarks.
Right, the lesson there is a big shift. Move beyond simple right-wrong scoring. We need systems that actually give credit, or at least don't penalize, models for correctly signaling when they're uncertain. It's about changing the rules of the game to reward truthfulness.
Second action, develop models with behavioral calibration. The focus in training needs to shift slightly. It's not just about maximizing accuracy, but about training models to be behaviorally calibrated, able to give the most useful answer that meets a specific confidence level, and crucially, knowing when to just say, I don't know.
So the lesson is, build models that don't just have internal confidence scores, but actually act on them appropriately.
Right.
Make risk-aware decision-making a core part of their behavior, giving users clearer signals about reliability.
And third, address pre-training factors directly. We can't ignore the roots of the problem. This means continuing to innovate on model architectures to better capture complex patterns and reduce poor model errors. It also means getting smarter about training data, maybe using techniques to ensure critical facts aren't just singletons, or developing methods to better handle inherent noise and ambiguity in the data.
Yeah, the lesson there is that even perfect evaluation won't fix errors originating from fundamental statistical limits or architectural flaws. We need progress on all fronts. Better base models and better evaluation. Okay, now for everyone listening, what can you do? First, and this is maybe the most immediate thing, cultivate critical consumption of AI outputs. Always remember that current LLMs are often incentivized to guess when they're unsure. Don't just blindly trust everything they say, especially if it sounds plausible but you haven't verified it.
That's such a key lesson. Develop that healthy skepticism. Cross-reference important information. Treat AI outputs as a starting point for critical thinking, not the final word, especially in high-stakes situations. Be an active, critical user.
Second action for users and businesses. Advocate for and test for uncertainty handling. When you're choosing AI tools or platforms, ask questions. Ask providers how they evaluate their models. Do they measure and report on hallucination rates? Do their models have ways to signal uncertainty? Prioritize systems that are transparent about this.
Exactly. The lesson is that your choices matter. As customers, you can create market pressure demanding more reliable and transparent AI. Ask providers, including platforms related to AI Coach by Anil Nathu, how they're tackling hallucinations and evaluating uncertainty. Support those who prioritize honesty.
And finally, leverage tools that prioritize accuracy and context. Seek out platforms and developers who are actively incorporating research like this, who are committed to mitigating hallucinations, and who aim for transparency and trustworthiness in their AI offerings.
The lesson here is simple. Vote with your feet or your clicks. Supporting tools and companies that prioritize ethically evaluated, behaviorally calibrated AI helps accelerate the entire field towards creating systems we can genuinely rely on. Your choices shape the future of AI development.
Well, thank you for joining us on this deep dive today. It's been fascinating and really quite critical, digging into why AI hallucinates.
Yeah, it's a complex topic, but hopefully this discussion, grounded in that insightful OpenAI paper, has helped demystify these errors. They're not random magic, they're understandable phenomena. And crucially, while maybe inevitable to some degree with current methods, there are clear steps we can take towards a more trustworthy AI future.
It really underscores that this is a socio-technical challenge, doesn't it? It needs changes in technology, but also in how we evaluate it, how we incentivize developers, and how we as users interact with it. It requires all of us working together.
Absolutely. Developers, evaluators, users, we all have a role in demanding and building better, more honest AI systems.
A challenging but hopeful path forward. Thank you for joining us today. Visit the AI Coach website for more AI insights.